Hello! In this video, we are going to prove the following theorem. Let G be a finite group. Then for all elements A and G, A has finite order. Now, let's first remind ourselves, since G is a group, this means that G is equipped with a binary operation. G is closed under that binary operation. Associativity holds. G has an identity element, and every element of G has an inverse. And since G is finite, this just means that the collection of elements in G is a finite set. And at this point, we have defined a notion of exponentiation for elements in a group. And the idea is as follows. Given a group element A to the power 0 is the identity element of the group. If we do A to the power of a positive integer, n, then just represents A multiplied by itself n times. And if we do A to the power of a negative integer, we'll say A to the power of negative n, where n is a positive integer, then this just represents the inverse of A, multiplied by itself n times. And we have proven the following property regarding exponentiation of elements in a group. Given a group element A, we have that A to the power of m times A to the power of n is equal to A to the power of m plus n for all integers m and n. Okay, now we're trying to prove for all elements A and G, A has finite order. So now, let's talk about what we mean by the order of an element in a group. Given a group G with identity element E, and given that A is an element of G, we say that A has finite order if there exists a positive integer n such that A to the n is equal to E. Now, if there exists a positive integer n with this property, then there exists a smallest positive integer that has this property. That just comes from the well-ordering principle. And so, the order of A is the smallest positive integer m with this property. Otherwise, we say A has infinite order. So in other words, to say A has infinite order means there does not exist a positive integer n with this property. Okay, so now let's get into proving this theorem. To start out the proof, let's consider a finite group G with identity element E. And from here, we want to show for all elements A in G, A has finite order. So since we're trying to prove a same about every element of G, let's give ourselves an arbitrary element of G. I'll call it A. And from here, the whole goal is to show that A has finite order. So we are going to assume for a contradiction, we instead have that A has infinite order. And to reach a contradiction, the idea is to consider the following function. We consider the function f from the positive integers to G. That's given by mapping each positive integer n to the group element A to the power of n. The claim is that we can show that this function is injective. So to prove that this function is injective, let's give ourselves two arbitrary positive integers, I and j, and suppose I is not equal to j. To prove injectivity, we would like to show that f of I is not equal to f of j. So, assume for a contradiction, we instead have that f of I is equal to f of j. In other words, we're saying a to the power of I is equal to a to the power of j. And to reach a contradiction, we are going to split this up into two cases. Either I is greater than j, or j is greater than I. Let's first consider the case I is greater than j. Now, if I is greater than j, then what happens? Well, notice, a to the power of I minus j can be rewritten as a to the power of I times a to the power of negative j. That's just applying the rule that we have for exponents here. But then, we know that a to the power of I is equal to a to the power of j, so this is just a to the power of j times a to the power of negative j. But then, applying this rule again, this is just a to the power of j plus negative j, or a to the power of 0, and from the definition of exponentiation, we know that a to the power of 0 is the identity element. So this shows that a to the power of I minus j is equal to the identity element. Or in other words, we have that a to the power of a positive integer is equal to the identity element. And that means that a has finite order by definition. But this contradicts the fact that we're assuming a has infinite order. So this completes the case that I is greater than j. Now let's consider the case j is greater than I. Well then, what happens in this case? Well, if we compute a to the power of j minus I, we know that this is just a to the power of j times a to the power of negative I. But then we know that a to the power of j is equal to a to the power of I. So this is just a to the power of I times a to the power of negative I. And then this is just a to the power of 0, and a to the power of 0 is the identity element. So we get a similar argument that we did above. So this shows that a to the power of a positive integer is equal to the identity element. And that contradicts the fact that a has infinite order. So no matter what case we have, we reach a contradiction. Our assumption that f of I equals f of j led us to a contradiction. So we must instead have f of I is not equal to f of j. So putting this together, we have shown if I and j are any two positive integers, well then if I is not equal to j, then f of I is not equal to f of j. And that tells us f is injective. But since f is an injective function from the positive integers to g, and g is finite, well that implies the set of positive integers must be finite. Because in general, if we're given an injective function f from a to b, and we're given that b is finite, then these two facts imply that a is finite. And in fact, the number of elements in a is less than or equal to the number of elements in b. So this is the reason why we obtain that the set of positive integers is finite, but this is absurd because we know that the set of positive integers is infinite. Our assumption that a has infinite order led us to a contradiction, so we must instead have that a has finite order. And so we've shown if a is any element of g, then a has finite order. And that is exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.